Hi, welcome back to these videos about Speakerbench. This is another video about the box simulation, and here we are at the Speakerbench webpage, speakerbench.com, and we just click on the Datasheet Creator to get into the Creator, and we load a driver, and I showed you before you can load whatever, but you can also pick one from this table here. It can be handy. And this is the same driver that we've been working with, but you can pick any of the other ones if you like. And we just click on the box to go to the box simulator. And here we are, the driver is already loaded, and you can see the driver data here. And let's try to play around a little bit more. I mean, all the other apps in Speakerbench, they are kind of top down. You get from point A to point B and from point B to point C. But the box simulator is more like a playground where you try a little bit of this and that. So let me try to show you something. We will first take a look at these response curves and see that this is how, in this case, how the driver is initialized. It's not that bad. It could be a lot worse actually. If you pick one of the other drivers, you get a really crappy initial suggestion. But the first line is the box, and actually Speakerbench supports 3 kinds of box simulations, and I recommend the TNet. It's by far the best one. The simple one is back to old school Thiele small, and then we don't add any damping, and you should set the leakage Q, the QL, to 7. You know, that old rule of thumb. But it's available here for, let's say, backwards compatibility. The Footwork Model is a model that I made back in 2010, and it was presented at an AES convention in London in 2011. And it's an electrical circuit model, so it's a little simpler than the TNet, and that has some disadvantages which I can show you later. But for all intents, please use the TNet model. If you choose the Footwork model or the TNet model, then it's, in both cases, it supports that you can add damping material, and you can choose between plastic fiber, standard PET fiber for loudspeakers, or glass wool in different densities, 12 kilogram per cubic meter, 25, 50, or 100. 12 is probably a little bit loose, but you might come across it. 25 could be standard, 50 is quite dense, and I always think that it would be highly unusual for you to use high density glass wool, but it's here as an option anyway. We can add more damping materials to this if you supply us with the fiber data that we need, and we can test and verify that it works. Then there's a fill percentage, which is 0. And if you remember, I said the QB value is infinity. That's because we haven't added any damping material, so there's no absorption. But you can add damping material, and you would maybe type 20% damping material in. And then you have here the input voltage we talked about earlier. But we push apply, and now you can see that the QB is 13.2. So that added quite a lot of absorption. You can also see here that the fill, we know the density of the PET fiber, and you would have to add 9 grams. In reality, the simulator exaggerates the effect. You would have to add more damping material to get the damping that we simulate. And I think the reason is that we don't specify where to put the damping material. And we kind of assume it's in an optimal place where it has the most significant effect in the box. But obviously, if you add damping material, it cannot all be in in that optimal place in the middle of the box. So the simulation exaggerates, and in practice you would have to add more damping material. But that's why we chose just some kind of percentage. It's a little bit abstract, and you get a percentage to work with. So this is the special feature of Speakerbench, and you would use this feature whenever you're working with a driver where you already know the viscoelastic properties, the beta value that you get from going through the steps in Speakerbench. So that's actually the key feature of Speakerbench, that you can do this. In the next line we specify the volume of the box, and like I said, it's just VAS, so you should probably try manually to work with it and see what you get. But already adding this fill material will change, for example, the response and the group delay of the driver. Let's have a look at that, by the way. So we look at the delay, and you can see that it's now not so peaky anymore, and we can also see that it kind of has a little more round shape to it here. Let's try to go back. Fill is 0, apply, and you can see that now it kind of comes up, ding, and then rolls off like that. So it's kind of sharp, and the delay is more significant here. Yeah, so that's one important observation, that your box size and the box tuning and what you're going to end up with depends on the absorption in the box. And when you do that, when you have a driver with viscoelasticity, when you simulate absorption, this is the correct way to do it. And then the leakage loss should be ignored, basically. 50 might be a right number, but you could also write 1,000 if you wanted to. But if you're making a good box, you don't have a lot of leakage in the box, and you should put some high number in the leakage. That would be the correct way to do it. And then we have these ratios, Lx over Lz, the ratio of box width to depth, and Ly to Lz, box height to depth. And here it's a cube, but you would probably normally shape the box a little different. You would maybe make it a little narrower than it's deep, and a little taller. And a classical proportion would be 0.8 and 1.25. And then it's 1 deep, right? Let's try to do that. Apply, and then you go to the information tab, and you can see that now it's 18.7 wide, 19.3 high, and we kept the depth proportion at 23.4. So you can do that, and as a result of that, if you go to the SPL, this box mode, the first mode, is now at a lower frequency. It was 733, now it's 587. So that's because we made it taller, so the first box mode now comes at an earlier time. And yeah, so just be aware of that. So that was the box volume and proportions and the leakage. The final step here is the port, and we support 2 models for the port, a simple one and a transmission line model. When you simulate the port as a transmission line, you are looking at, let's say, the modes in the port, and that'll give you some effect in the port. And the port Q, we also have 100, but in reality it depends on how loud you play. If you're reaching turbulence, then obviously the port Q is suddenly very low. And here we have a 2-inch diameter port, which is kind of a little bit small for this driver. But you know, it gives the right length that fits inside the box. Okay. If we look at the SPL for the port, we can see that it comes up and down like that. Very nice. And if we change it to the transmission line model, we get the modes in the port. And these are real modes. I mean, they might not occur at exactly the right frequency or anything, but they're there. You know, you will find these modes, these port modes, in a real transmission line box. Especially if there's no damping, it'll be very, very much like this, and you get some bumps here on the frequency response. Right now, the port mode is above the first mode in the box. That's a coincidence. They could also be below. I mean, if I let's say if I chose a larger port of a box, 2.5 inches, that's 64 millimeters, it becomes larger in diameter and longer. And if we look at the information page, it's now 34 centimeters, so it's longer than the largest dimension in the box. It would have to stick out on the outside of the box. We can see that the first resonance mode is actually below the box mode. So that can happen. Just be aware of these modes in the port, that they play a role. And maybe that's also a reason why some people like to put the port on the back side of the box. Then these modes radiate towards the back wall and not straight to the listener. Thank you very much for watching, and please remember to sign up for our YouTube channel.